Hello guys, welcome to my video. So today, we're going to talk about the magnetism in physics. You must have noticed magnets at one point of time in your life, but do you know that these magnets play crucial roles in our daily lives? Well, in this video, we'll discuss some everyday example of magnets and the magnetic force produced by them. But before we started, let's learn a little bit about magnetic force. So, what is magnetic force? Magnetic force is a part of the electromagnetic force, which is one of the four fundamental forces of nature and is caused by the motion of charges. There will be a magnetic attraction force between the two objects containing charge with the same direction of motion, whereas objects with charge moving in opposite directions have a repulsive force between them. It is also defined as the attractive or repulsive form of energy that exists between the poles of a magnet and electrically charged moving particle. These moving charges create a magnetic fields, and the interacting magnetic fields give rise to the magnetic force. Now we have already learned about the magnetic force and fields. So, these are some of the uses of magnetism in our daily life. Actually, there are a lot of the uses in this world, but we are only going to talk about these two, which is compass and the trains. But before that, let's watch a short video about how does compasses works. So grab some popcorn and enjoy.
How do compasses work? Compasses have helped lost souls find their way home for more than 2,000 years. But how does a little metal needle actually know which way is north? In a sense, the Earth itself is a giant magnet. It has a North Pole and a South Pole, and those poles can interact with other magnets in the same way that the magnets on your refrigerator can. Opposite poles attract, while like poles repel. The needle in your compass is also a tiny magnet, made from magnetic rock like iron and suspended in liquid so that it can swivel freely. And so, when you hold your compass level, the north pole of the needle naturally aligns with the opposite pole of the Earth's magnetic field, a spot on the top of the globe that we call magnetic north. Unfortunately, for some explorers, Earth's magnetic North Pole doesn't exactly align with the geographic North Pole, otherwise known as true north. While true north always sits at the top of the Earth's axis in the middle of the Arctic Ocean, the magnetic North Pole is about 1,000 miles south in Canada. To make things even more complicated, magnetic north has an annoying habit of moving around as our planet's magnetic field warps over time. By some estimates, the magnetic North Pole has moved more than 600 miles towards Siberia in the last 100 years. It may not be 100% accurate, but the swiveling little magnet in your compass is still a pretty reliable bet for finding your way home. How compasses work.
Now, we are going to move on to the next level, which is the explanation. As we know, compass is a tool for finding direction. It has a magnetic needle mounted on a pivot, or short pin. The needles can spin freely, and it is always points to the north. So, I have a question for you guys. Have you ever been on a hiking or a camping trip, maybe with your family or even with your friend? Then if you did have, maybe at some point, you must have used a compass to help finding your way, because a compass always points to the north. But have you ever wondered why is it so? Well, it is all caused by the power of magnetism. A magnet is what makes a compass point to the north, and the small magnetic pin in a compass is suspended so that it can spin freely inside its casing. In response to our planet's magnetism, a compass needle aligns itself and points toward the top of Earth's magnetic field, giving explorers and lost souls a consistent sense of direction. So, how does this magical thing works? A compass points north because all magnets have two poles, which is a north pole and a south pole. The north pole is attracted to the south and vice versa. The Earth is a magnet that can interact with other magnets in this way, so the north end of a compass magnet is drawn to align with the Earth's magnetic fields. As we can see, in the image below are the examples of the magnetic flow between the Earth and the compass. While a compass is a great tool for navigation, it doesn't always point exactly north. This is because the Earth's magnetic North Pole is not the same as true north, or the Earth's geographic North Pole. The magnetic North Pole lies about 1,000 miles south of true north in Canada, and making things even more difficult for the compass-wielding navigator, the magnetic North Pole isn't even a stationary point. As the Earth's magnetic field changes, the magnetic North Pole moves, This difference between true north and the north heading on a compass is an angle called declination. Declination varies from place to place because the Earth's magnetic field is not uniform, it dips and undulates. These local disturbances in the field can cause a compass needle to point away from both the geographic North Pole and the magnetic North Pole. According to the United States Geological Survey, at very high latitudes, a compass needle can even point south. By using charts of declination or local calibrations, compass users can compensate for these differences and point themselves in the right direction. Congratulations! You now have learned about the beauty of compass. So right now, I would like to take you to travel to the past with me by this amazing Maglev trains. Awesome, right? Now, we are going to watch another short video about how this Maglev trains works. So just sit back and relax.
What is a maglev train? The word maglev comes from the combination of magnet and levitation. Maglev trains take advantage of a physics principle that says two like magnetic poles will repel each other. For instance, the north pole of one magnet and the north pole of another magnet pointed at each other will push away from each other. But if we put a south magnetic pole and a north one together, they will attract. Maglev trains take advantage of both of these ideas, not only to provide levitation, but also propulsion. In order for the train to levitate, the two like poles are forced to repel each other like the magnets shown here. To provide propulsion, the train is outfitted with a north and south pole magnets along the sides. The track also has north and south pole magnets whose poles can be switched quickly. As the poles are switched, the train is attracted to and then repelled by the same magnet. The faster the poles switch, the faster the train goes. Now you may be asking yourself, why is all this necessary? We already have trains. Maglev trains offer one key advantage over typical rail and high-speed rail, and that is minimal resistance. Unlike other trains that must stay connected to the rail, Maglev trains can float above the rail, only having to overcome air resistance. The only problem with Maglev trains are that they are very expensive, costing between $50 and $200 million per mile. Compare that with a reported $82 million for high-speed rail and a meager $2.5 million for typical rail service. Maglev trains still may have a home if the Hyperloop ever takes off, but that's a video for a different time.
From the video, we already know that this Maglev train are so cool and they can just bring us from New York to Los Angeles in just 7 hours. This is literally the coolest things ever. Moving on to the explanation on Maglev trains. So, Maglev trains use the magnetic forces to remove the frictional forces between the track and the train. By allowing the train to float on a cushion of air, these levitating trains are able to react speeds of more than 310 miles per hour. Wow, so incredible, right? There are two types in magnetic levitation technology, which are the first, electromagnetic suspension, and second, the electrodynamic suspension. Electromagnetic suspension is the electromagnets inside the train that are attracted to a magnetically inductive track, while the electrodynamic suspension is the magnetic fields that are used to induce currents in metallic conductors. So next, we are going to learn more about the suspension system. So the first one, which is the electromagnetic suspension, is the electromagnets that are attached to the train that allow the train to levitate above a steel rail. This is more unstable than an electrodynamic because the system's major advantage is that it works at all speeds. It is also because the magnetic forces vary inversely with the distance cubed, which are the smallest changes in the distance between the track and the electromagnets that produces greatly different forces. Therefore, maintaining a precise distance between the track and the train is the biggest challenge for electromagnetic suspension. In the last one, which is the electrodynamic suspension systems, the train levitates by a combination of attractive and repulsive magnetic forces. The magnetic fields that are used in an EDS system are created by using either permanent magnets or superconducting magnetics. The major advantage of this system is that the design that allows for the correct distance between the train and the track to be held in place by competing attractive and repulsive forces. The biggest drawback, however, is that the system does not work at slow speeds. Thus, because of this, wheels must be used as the system slows down or as the train is accelerating to the point where the magnetic fields can support the weight of the train. And now, sadly to say that we have already reached the end of our destination. Thank you so much for listening, and hopefully these information will help us in understanding more about the beauty of physics. I hope you guys enjoy this travel and see you soon. Bye.